So every Wednesday I'll take double class. Is that okay? And some of you have class after this, but I have to also move on. So Wednesday your class will be till like 5:30 maybe. Okay, because I just want to wrap up with magnetism. Magnetism syllabus is manageable. Because the chapters after those are like really small, but magnetism is like really large. It's 3 chapters together. There's electromagnetic induction. There is Fleming's left-hand rule, and there is also something called charges and magnetic fields. So তিনটা chapter মিলে magnetism হয়. On top of that, there's an additional chapter called AC currents. It's an additional part of magnetism. So ওগুলো যদি শেষ হয়ে যায়, we have for very small chapter, not basic chapters, but small chapters: quantum physics, nuclear physics, medical physics, and astrophysics. Okay, these are standalone, so you can do them individually. Anyways, let's start. So we were doing electric potential last class. What was the purpose of going through all of these? Because Ajke we'll see how it works in a non-uniform field. And the thing is that if you don't understand uniform field, you will struggle with the non-uniform field. So uniform field mode, I tried to explain to you the idea that if you have a charged particle in a field, and if it's moving against the field, it will gain electric potential energy. And if it moves with the field, it will lose electric potential energy. So if you go against the field, you will slow down. And if you go with the field, you'll become faster. If you can understand that idea, then rest should be very manageable. And also, there's this very underrated equation out there, যেটা তোমাদের use করতে হবে, which is QV. Okay, so this is still going to be very helpful here. It's if you want to find the amount of energy needed, you multiply the charge with V here. Just act a heads up there, the V that you see here is actually what V? Del V. Change in potential. Okay, so how much change is taking place out there? Clear? So typically we assume it goes from 0 to we just say 50 volts, but like in a battery, there are 2 terminals out there, right? In a 50-volt battery, the positive terminal is how much voltage? Plus 50, and the negative is what? 0. Just if I want to find the energy in the battery, we just use QP. But your charge may go from one potential to another potential. Change, the absolute change. Okay, so yeah, anyways, let's see what to do with non-uniform field. So non-uniform fielder মধ্যে how do we incorporate the field potential here? So yeah, this is electric potential once again. But this time, this is for a non-uniform field. So how do you find and define electric potential in a non-uniform field? So I'll make this simple for you. Just remind me, what was the definition of gravitational potential? Gravitational potential is symbol that they start for. What's the symbol for gravitational potential? That's why I started with the symbol, because I know that symbol. What's the symbol for gravitational potential? Phi. Okay, phi. And what's the formula? Yeah, Gm by d. But that's not it though. What is it? Minus. And this is always minus. Okay, because you take infinite as 0, and every value beneath that is going to be a negative number, right? The negative does 2 things here. It shows that you're losing energy, because when a charge moves towards another mass, a mass moves towards another mass, it loses potential energy, right? That's negative. Also, the other fact is that we take which part to be 0 in our system? Infinite. So everything beneath is going to be 0. It's the same here as well. But can you remind me, what was the definition? What is the definition of gravitational potential? Perfect. Okay, that's exactly the definition. Is the amount of work done per unit mass to bring it from infinity to any point in the field. So how much work you need to do, right? Electric potential is the same thing. So what is the definition of electric potential? It is the amount of work done to bring a unit what charge? Positive charge, right? To any point in an electric field. But this leads to a complication. What is it? For gravitational field, the force was only what in nature? Attractive, right? But in an electric field, what can the force be? Both attractive and repulsive, right? So should we have a minus here, or can it be plus or minus? Plus or minus. Okay, so the formula is going to be both the signs. Anyways, what is the definition of electric potential? Not energy, just electric potential. Okay, It is the amount of work done per unit charge to bring it from to any point in an electric. Right. So electric potential হচ্ছে non-uniform field এর জন্য this is a definition. In fact, this is a definition for any electric potential. But on the non-uniform field মধ্যে we do have an infinite point, right? So এখান থেকে নিয়ে আসা হচ্ছে. So what is the formula for electric potential here? Electric potential is given by V, and V is equal to KQ by D. That's the formula for electric potential, which can be further broken down as what? Q divided by 4 pi epsilon D. This is the equation for electric potential. Electric potential for what? A non-uniform field. Okay, not just any non-uniform field, a non-uniform field around a what mass? Point mass. Okay, or point charge. Sorry. So yeah, this is your potential. So what does it actually mean? ওটা একটু বোঝার চেষ্টা করি. So imagine this. Okay, to carefully দেখো আমরা ম্যাথ করা স্টার্ট করব. So you have a charge here. Okay, just random একটা point mass and charge. Okay, and there is another charge in its vicinity, but in the area around it. So I hope you understand that a charge at চারিদিকে, there's a region in which it experiences force or exerts force. What do we call that? What do you call that region? Electric field, right? So this place is the electric field. Is it uniformly distributed, or is it different in different places? Different in different places, right? Where is it strong? Where is it weak? Right, so it is something like this, okay? It's very strong near the charge, and the further you go away, what happens to it? It becomes weak, right? So this is the electric field out there. So, question for you, okay? If I had to take a charge, let's say this is positively charged. If I had to take a positive charge from this location, if I had to take a positive charge from this location to that location, let's say the distance traveled here is this. Okay, the amount of work that I need to do, will it be the same or will it be different for you to take the same charge to another location of the same distance away? মানে আমি যদি এখান থেকে এখানে নেই, the amount of work that I do, same distance যদি ওদিকে যাই, do I do the same amount of work, more work or less work? Why? হ্যাঁ, তো আমার যদি এখান থেকে এখানে যেতে ওয়ার্ক ডান হয় 10 জুলস এই ডিসটেন্সের জন্য, রাইট? আমি যদি সেম ডিসটেন্সে এখান থেকে এখানে যাই, আমার কি ওয়ার্ক ডান 10 জুলস হবে, নাকি লেস হবে, না মোর হবে? লেস। আচ্ছা, কেন? অল্প একটু ফোর্সে চলে যাবে। Why? More work to travel same distance. So you're going, the field is pushing you, right? So if the field pushes with less force, will you do less work or more work? Yeah, the field is pushing me, right? And the field is giving me energy. So the amount of energy I gain here, by the way, let's just clarify something. As you go from here to there, you're losing electrical potential energy and gaining what energy? Kinetic energy, because it's repelling you, right? So the amount of K you gain from here to there, will it be the same as the amount of K that you gain from here to there, like same distance? Should the K gain me more or less? Less. Achha, tumi consistently less boltes, but what's the reason? Sir, kinetically less. Okay, you're right, Oliver. Yes, the answer is going to be less. And the reason behind that is the further you go away from a charge, what quantity decreases for shear? The force. And what is the formula for work done? Force into distance, right? So the thing is, equipotential lines, if my equipotential line is here, representing a certain amount of work done. Okay, let's say this is my equipotential line here, and it's representing a certain amount of work done. To do the same amount of work again, do I have to have a circle with the same gap, or does the circle need to have a bigger gap? That was my question actually. So the answer is the circle needs to be further away. And the reason behind that is as you go from here to there, right, the force is less. But equipotential lines are drawn based on all gaps having what value? Same one. I'm going equipotential lines, so you have to go back. We are still not covered this part. Let me just go back one more time. Is it same change in potential? Or questionটা হচ্ছে আমি যদি হচ্ছে একটা ইকুইপোটেনশিয়াল লাইনে যে গ্রিন লাইনটা আর রেড লাইনের how do they compare? What increases? So that my question is এখানে distance বেড়ে গেল, right? Distance কেন বেড়ে গেল? Force decrease, right? So what does the gap actually signify? Force. Work done. So from here to there, the change in energy is the same as there. Okay, so I'll give you an MCQ. Okay, the gap from these lines, the equipotential lines, right? The gaps represent what? The gaps represent change in energy, change in potential, change in length, or change in force. What are the gaps drawn based on? The change in force, change in potential, change in energy, or change in length? Yes, it's work done. Okay, so the work done between any two equipotential line is going to be what value? Same value. Why? Because work done is what? Force into distance, right? So in a uniform field, you'll find that all the gaps are what value? Same value, because the amount of force is same, so amount of work done is what? Same. But এখানে তোমার তো শুরু থেকে force is very high, so you can do a lot of work in a small distance. But to do the same work later on, what distance do you need to cover? More distance. তোমরা কি বুঝছো? আবার repeat করি, এই যে it was here. Why do we have these values? Okay, so value গুলো কি represent করে? The gaps that you see here, they represent the amount of energy change. Okay, so when I draw an equipotential line, কি mean করতেছে কেমনে হচ্ছে তোমার এটা চেঞ্জ হচ্ছে, এই energy change হচ্ছে, right? So if I go back to this diagram here, like what we were doing today, can you now again rethink and tell me যে এখান থেকে এখানে যে ডিসটেন্সটা, এখান থেকে ওই ডিসটেন্সটা কি হওয়া উচিত? বড় হওয়া উচিত. And the reason behind that is, what's the formula for work done? The formula for work done is force into distance, right? Regardless of what kind of scenario it is, that's the formula. Work done equals to force into distance. I want to do the what amount of work for every gap? Same amount of work. Since the force is decreasing, what amount of distance do I need to cover to do the same amount of work? More distance. So the further and further you go away, you'll notice the distance increases. Not only that, the distance increases in what manner? Exponential manner, which is a reflection of the fact that the force decreases in what manner? Exponentially. Okay, so you'll find that the gaps are like very close and suddenly they're big, and then very suddenly they're really big. And the reason behind that is the force decreases exponentially, right? So anyways, we have done from just recapping it. So how do we incorporate that here? So the question that we're going to solve today, and next question, you're lucky about this thing, a topic, there's only one question they ask you, which is, as a charged particle here, the charged particle moves from here to there. What is this change in energy or velocity or whatever the quantity that they're asking you? So they want you to find out the variation in properties of a charge moving within a field, speed, okay? And তার জন্য আমি তোমাদেরকে হচ্ছে last class I made you do this question, because if you can understand the uniform field, it's easy transfer to non-uniform field. So the question I asked you last class here was what? That you have a charge here, the charge goes from where? Here to there. How did you find the answer? So what you found was, or at least that's what we were supposed to do, we had to find the what between these 2 points, the potential difference. And using the potential difference, we could find the amount of what here? Work done. And that would be either gain or loss depending on what your scenario is. So if your object is moving with the field, right, it's going to lose potential energy and gain kinetic energy. So a classical example that they give you in your exam is that there's a proton that you're firing towards the nucleus. It's like a proton where nucleus is attached to say. How far from the nucleus can the proton reach before it stops and goes back? So it's a very important, math and physics. I'm origin to believe. So there's this thing called the Rutherford scattering experiment. And Rutherford scattering experiment was there was a nucleus, and we fired alpha particles at it, and we wanted to see like how far could the alpha particles go before they stop. And we found something strange. We found that every time you fire an alpha particle, it'll go very close, right? And then it'll come back again the same way. It didn't collide with it. What did it actually do? So this is positive, right? So as the alpha particle starts to approach your nucleus, it starts to what every time? Slow down, slow down, slow down. And it, just runs out of steam. It's just losing all the energy and it stops. But does it stop and stay there? No, right? So wouldn't the repulsion take you back again? So the math they want you to do is to find out how far to the nucleus can an alpha particle go with a certain velocity you have. So I'm going to do the alpha particle fire query at a velocity of 4 into 10 to the power, let's say 7 meters per second. How close to the nucleus can you actually go? And they tried doing this and they realized that it keeps going further and further and further before it ever actually hits it, which kind of tells us that the nucleus must be of what size? Really, really small size. But it always stops and comes back, which means the nucleus must be of what charge? Yeah, positive charge, and not only positive charge, really high positive charge. And that those were the findings of Rutherford scattering experiment. A very small nucleus with a lot of charge in it, right? So this math is actually based on that, okay? And past paper mode, you'll only find this math. Same as gravitational field. You remember what the math was? You have a rock coming towards the earth. You have to find out what the speed of the rock is, or if you throw the rock outwards, how far can it go? Basically that, okay? So I'm gonna directly at the question for both. But yeah, just before I start, just quick reminder, this is the value of V. And V money key, I can find the value of my potential here. So for example, this one is 100 volts. This one is 200 volts, just random numbers. How do I find these values? V equals to K, Q by D. And that's the value that you have for each line here. So line value formula. So let me show you a math that I think would be the best way forward. Okay, let's have a look here. An alpha particle is fired towards the nucleus of gold. Find the speed needed to reach the surface of the gold atom. The alpha particle starts 10 centimeters from the center of the gold atom. So you have to find out what is the speed needed to reach the surface of the gold atom. There are other information that you need, gold atom size and everything. So then I'll give you another question to try. Okay, so look, understand the question. It says that there's an alpha particle fired towards a gold nucleus. So gold nucleus, and whenever you have a gold nucleus, we assume that the gold nucleus has a charge where in the nucleus? Center. So Earth mass we assume that the surface is just extra additional part of the system, but all the charge happens to be right at the center. And it says that the gold atom radius is 1 into 10 to the power minus 8 meters. This radius here is 1 into 10 to the power minus 8. If you carefully try. Now we have an alpha particle that's coming from where? Far away. And how far away? This is your alpha particle. And it happens to be 10 centimeters from the center. So the alpha particle is going to come all the way from there, which is 10 centimeters from the nucleus. And this is positive 2 charge, and gold is what charge? Nucleus plus 79. Okay, so gold is 79 and alpha is plus 2. And we have everything else provided here, mass and everything. What are you supposed to find out? Find the speed needed to reach the surface of the gold atom. So how much speed should my particle have here so that it can go all the way and reach the what of the gold atom? The surface. That's the question. Okay, are you okay with the question? I'm the question to answer kora bujhabo abar boli I'm going to fire an alpha particle. So alpha particle to eta korte pare, it'll come here, stop and go away, or it can come here, stop and go away. I want to give it enough energy so that it can reach the what of the atom, surface of the atom. So how can I do that? So can you tell me how would I be able to do this math? I mean, context the sector. Imagine this is the table that we have here, which is where the alpha particle is right now, and that thing at the ceiling is the gold atom. I want to throw a ball from here so that the ball goes and just hits the ceiling. Just hits the ceiling, right? A math forget this chapter. Yeah. So I've given you the height. I just want you to find me the velocity at which I should throw this so that it goes and just barely hits the top. Acceleration. 9.81. But I mean, normally, a question. Just Earth context. At the moment, I'm going to take a ball in my hand right now. I'm ball throw so the ball goes, let's say, 2 meters and just hits the thing at the top. At what speed should I throw this ball? That's the question. Yeah, V equals to U plus 80. Can anyone tell me in terms of energy, how do I do this math? Yes. So as you throw this thing, right, it loses what as it goes up? K. And what does it gain in the process? GP. So I'll just do GP gain equals to K loss, right? Exactly same math data. There's nothing different here. It's just sideways draw kora. So the math is basically okay. So I'm going to throw this ball all the way up to the top. You need to find out at what speed should I throw so that it just goes and touches the top at the surface, right? Now, a couple of things before we attempt this math. What is the ball losing as it moves towards the nucleus? Kinetic energy. What is it gaining as it moves towards the nucleus? Electric potential energy. So how do I find electric potential energy? Now, if you understand, I haven't given you a formula for electric potential energy. I'm not giving you a nice little say for non-uniform field. There's no electric potential energy equation out there, but there is actually. So how would you do this math? But electric potential energy is the way so that আমি kinetic energy equal V বের করতে পারি। আচ্ছা, yes, করতে পারো। E equals to QV, right? E equals to QV, তারপর কি করবা? Yes, very good. So আমরা V jump, we know how to find V, and that's what the chapter is focusing on. So what I'm going to do right now is I will find the value of what here? V1, and I'll find the value of what here? V2. These are called potential. And then I'll find the what between these two things, potential difference. And when you multiply potential difference with charge, what do you always get? When you multiply potential difference with charge, what do you get? Electrical energy, right? And that's how you can find out the KE out there. So I'm trying to give you parallels to something we've already done. Gravitational field. Gravitational field, what did we find? Gravitational potential energy or just gravitational potential? Mass, right? Which a formula phi equals to what's the relationship between gravitational potential energy and phi? Bolo ekhane ekta mass thakbe, mass ta koi jabe? Yes, phi m equals to gp. So same bhabe EP ta ki parallel? EP er jagay v hobe, eta ki hobe? Q. You understand? They're very similar. That's why if you understand gravitational field, right, you'll find this is actually the same thing, just massive data charge. That's it. Okay, so let's try. So first, step number 1, what do we do? So online, a couple of you gave answers. They're very close. So first, we'll find the potential at 1. How do you find that? KQ divided by D. And always remember the potential is from like AJ. Infinity থেকে এই পয়েন্টটা আর ইনফিনিটি থেকে এটা। আমি কি সেন্টার অফ চার্জ থেকে আমার পয়েন্টে যাই বা ইনফিনিটি থেকে আমার পয়েন্টে আসি? ডাজ ইট মেক আ ডিফারেন্স? আমরা তো ইনফিনিটি থেকে আসি, বাট আমি সেন্টার থেকে যদি যাই বা ইনফিনিটি থেকে যাই, ডাজ ইট মেক আ ডিফারেন্স? No, because at the end of the day, what do we want? Change. Okay, so change from there and change from here, what would we say, right? When I'm doing GP measure query from the floor, right, and I do my math, what if I consider the ceiling to be my floor and I did my math? It wouldn't be any different because at the end of the day, we're finding the what in energy change, right? That's why I can take infinite now, which wouldn't make a difference to our calculation. And K is how much? 8.99 into 10 to the power 9. into charge. এটা হচ্ছে কার ফিল্ডে are we moving? Whose field are we moving in? The atom, right? So এখানে কি হবে? Plus 79 হবে না plus 2 হবে? Plus 79 because we are falling in the field of the positive charge, right? So এটা হবে হচ্ছে 79 into what is the charge? 1.6 into 10 to the power minus 19. I hope you guys understand by now that plus 79 is not the charge of a gold nucleus. What is that? It's a relative charge, right? Relative charge is a charge compared to the charge of an electron. The actual charge of a gold nucleus is that, right? Do you remember? Okay. Divided by distance, the distance the surface is 1 into 10 to the power minus 8. So that'll give me a potential. Now V2 kemne beri korbo? Same hobe. V2 is going to be KQ divided by D, and it's going to be the exact same thing with one small difference. This is going to be how much? 10 centimeters. So 10 centimeters jodi hoy eta is going to be 10 divided by 100. So it V dibe. So this will be my two voltages out there, or potentials out there. Can you tell me what these values are? 3.6. Okay, and the second one? Minus? Minus 6. Why is it 79? 79 because we are finding the field of the positive charge here. This is 79, right? So we're finding the potential in the region around the 79. 79 is the charge of the gold nucleus. Yes? From the center to the surfaces. No, V2, V1, just number this. It could be anything. Yeah, because at the end of the day, I'm going to change the key. Absolutely. Plus minus the matter. Plus minus the decide by either it's moving with the field or with the, against the field. So yeah, so I'm going to find the change in potential here, which is going to be, I think, 11.36. Because bakita to kubi choto, right? So 11.36 volts is my potential difference. Then how do we do the math? What do we do next? Yes, so we're going to multiply this change in potential. So next step, we find the electrical potential energy, which is going to be Q into del V. Now this Q happens to be which Q? The one that moves, right? The one that's actually experiencing the energy change. So a question was who's moving? Plus 79 or plus 2? Plus 2, right? So this is going to be 2 into 1.6 into 10 to the power minus 19 into 11.36 volts. That will give you your change in EP. So how much electrical potential energy is changing here? Tapor tomdeke ami ekta question korbo, but age eta ekটু wait করে নিও. Into 10 to the power minus 18 joules. Acha. My question for you, okay? Is this a gain in EP or a loss in EP? Chinta kore bolo. Is it a gain in EP or a loss in EP as it moves from V2 to V1? Yes, gain. No, loss can have yeah, it's going this way, right? So it's going to gain electric potential energy and it's going to lose what? K, right? It's like a ball thrown up in the air, right? We are going against the field. So when you go against the field, what do? You gain potential energy and you lose K, right? So this is EP gain. And the EP gain must be equal to what loss? Yeah, so hence EPE gained is equal to K. Oh, you thought in terms of K, correct? K is actually loss, you're right. So this is going to be 3.64 into 10 to the power minus 18 equals to K is going to be half into mass of alpha particle is 4.6. 4 into 1.67 into 10 to the power minus 27 times V square. So if you want to reach the surface of a gold nucleus from 10 centimeter far out, this is the speed at which you should be moving. How much is it? 1.09 into 10 to the power? Oh, you didn't root. 3 point? That's a math. Okay, so I'll check with the same answer as maybe 3 point. ঠিক আছে. In a vacuum. Yeah, and our syllabus only assumes it's a vacuum. But let's say you're underwater, you're in a static field, the value changes. Okay, so there you go. In potential diagram to draw because I'm still not convinced of Buchila. So this is the nucleus or the place where the charge is, and you have these lines around them called the what line? Equipotential line. Equipotential line is a line along which the value of potential is what? Where? Same. That's the first thing. Second thing, what does the gap between two equipotential lines represent? Yeah, it's the change in energy from one to the other, and it represents what change in energy? Equal changes in energy. That's why you'll find that to do the same amount of work from here to there, you will have to cover more distance and more distance and more distance as you go further out. And the logic behind that is the further you go, the force decreases. So to do the amount of same work, you need to cover more distance. Work done is equal to force into distance. Summary line গুলো হচ্ছে এটা draw করার একটা conventionটা কি করা হয়েছিল when they started drawing equipotential lines, they decided that we'll draw the lines in a way where each line gap has what value, same work done, so that you can picture is the field getting weaker or stronger. But I'm যদি এভাবে draw করি just সব same gap and I show it to someone, right, they can't really understand what's happening, how the field is changing. But if the lines start to separate out like that, and we understand that each gap represents the same amount of work done, we understand যেহেতু বেশি distance নিচ্ছে, definitely এখানে কি কমে যাচ্ছে? Force. To incorporate both the ideas into one diagram, they started using these lines called equipotential lines. Okay, তোমাদের draw করতে হয় এটা. In fact, there's this complicated diagram where you have to draw the equipotential line between two charges. I haven't seen it yet. তোমাদের syllabus-এ Excel আসে, তো আমি তোমাদেরকে দিব একটু পরে try করার জন্য. Okay, ওটা পরের ব্যাপার. So before that, I want you guys to copy this. First take a copy now, and then I'll give you another math to try. Done? Sure, before I do some questions, I'll do the graphs. So next to page 106, if you have a blank space there, we can graph the draw করো. So it's graph for electric potential. Okay, let's try to understand the graphs here. এখানে হচ্ছে total combination হচ্ছে চারটে graph হবে. The four graphs are, what is the graph going to look like for a positive charge moving towards a positive charge? So আমি বলে নিই তোমরা একটু চিন্তা করো. So positive charge moving towards a positive charge. And what do the graph look like for a negative charge moving towards a positive charge? And the other two would be positive charge moving towards a negative charge and a negative charge moving towards a negative charge. Four different combinations, okay? Right, so can you guys plus moving towards plus, what should the graph look like? So how would the graph look like? Repulsion to Janu. That's the question. So the question is, do you gain potential or lose potential? Simple question. As a plus move towards the plus. Yes. তখন তো তোমার গ্রাফ কিরকম দেখতে হবে? How would the graph be? Would the value increase or decrease? Increase, right? So এরকম দেখতে হয়. And the closer and closer you get to the surface, the value gets higher, but you can never reach what value though? So এটা যত কাছে থাকবে, it starts to become asymptotic, okay? So গ্রাফটা এরকম দেখতে হবে. And similarly, if it was negative charge, how would the graph look like? Exactly same thing, but কি হবে? Mirror. আচ্ছা, so যেদিকে হবে এদিকে, and the negative value here indicates what's happening. It's losing potential as it's getting closer and closer to the positive charge, right? So আবার দেখাই, if you have a negative charge moving towards a positive charge here, does it gain potential energy or lose potential energy? Lose, because your charge is going with the field. But if it's a positive charge moving towards a positive here, what is it going to do? Gain energy, because it's going against the field, right? So the graph looks like this. However, this graph has something additional, which they ask a lot of questions, which is, what does the gradient of the graph provide you? So listen carefully, okay? The gradient of this graph is actually very useful. So I want you to predict, first of all, formula key, V equals to KQ divided by D. My question for you is, what is going to be the gradient of this graph? What does it give you? Force. What does the gradient of this graph give you? Electric field strength. Yes. Okay. Why? Because what is V? V hoche potential, and this is D, right? What's V by D? Electric field strength. Remember, F by Q, V by D, field strength. But there's a problem though. Problem hoche, is this gradient here positive or negative? Negative, right? But তোমার তো হচ্ছে এখানে field strength বের করতেছো for a what charge? Positive charge. Then the value be positive. Do you follow what I'm trying to say? What's the formula for the electric field strength of a +2 charge? E equals to K Q divided by D square. So I mean, K nivo, what's my charge going to be? +2 divided by distance is going to be D square. It is the plus, so shouldn't my electric field strength be a positive value? But then when I find a gradient here for the positive charge, I find the gradient happens to be a what value? Negative value. Isn't that contradicting it? So therefore, what's the actual definition of this gradient? So it turns out, yes, exactly. So the gradient of this graph gives you what? It gives you negative electric field strength. Okay, so electric field strength, one version to provide for it, negative version, electric field strength. And it's a very common question in your past paper. For 1-2 marks, they'll ask you, what does the gradient of the graph give you? And the answer is negative electric field strength. Okay, so negative cannot because if you look at the value is fine, but there's a small discrepancy here. What is it? It's opposite sign. So how do you correct it? By putting the right sign. Okay. So yeah, this is the gradient of the graph. So you'll find that the gradient of these graphs provide you electric field strength. And that is going to be a very useful tool for what we're going to do next, okay? So if you find a gradient here, you will find that it provides you electric field strength. Not just electric field strength, negative version of it, okay? So this is del V by del D, and that's going to be minus E. Right, so that's the graph for what here? This is the graph for your positive charge. Now, how would the graph pair look like for negative? So negative এর জন্য আমাকে একটু বলবো এখানে কি modification করলে I can make this graph negative. So যে negative গেল এখানে. What other changes do I need to make here? Yeah, so your negative charge has to be on the top and the positive charge has to be the bottom. So negative charge যখন negative charge এর দিকে যায়, what does it do? Gain potential energy. And when the positive charge moves towards the negative charge, it loses potential energy, right? So that's the only difference. Everything else is the same because the value would still be the same. Okay, so we have this here. Our right. So one last graph. I mean, I'll give you time to copy that, but main. What is the graph going to look like between two charges for electric potential? Say এটা তোমাদেরকে একটু চিন্তা করে দেখো পারো নাকি? I don't want you to memorize these things because they can be so random. You memorize 10 of them and then another one shows up, right? So try to understand and try to come up with the answer. So my x-axis here is distance. How would the graph look like between two positive charges? U shape. There'll be but that's electric field strength, right? This is potential. Potential in null region to kichu nai. U shape. Further away decreases. So it so is it going to be a 0 or is it going to be a low value? Not 0. Acha. And then it goes the other way. No, আমরা তো net potential draw করতেছি। একটু উপরে non-zero. এরকম আচ্ছা কেন এরকম what's the reasoning oh no আমরা point charge দিচ্ছি তো একদম so point charge তো it can touch okay so yeah you can do this এই যে এখানে এটা করতে পারো that would be more appropriate অসুবিধা নেই হ্যাঁ but what about the center so what's the formula for electric potential ওটা imagine করি E equals to or V sorry V equals to K Q by D right আর এখানে হচ্ছে this is going to be V equals to K Q by D and let's say the distance is that so I want to find out the net potential at a point there so should it be zero or should it be a low value here low value Acha. So the thing is it can be anything but the main thing that you need to look for is the graph must be I'm not taking hocche na but the graph must be perfectly what here flat and the reason behind that what is the gradient of this graph electric field strength right and the electric field strength between two positive charges right at the center what is it zero what is that point known as the null point right so এখানে যেটা null point হবে you'll find sorry করবে না ওকে বিকজ জিরো সো কেন টাচ করবে না আমি একটু এক্সপ্লেন করি এটার ভ্যালুটা হচ্ছে পজিটিভ এটার ভ্যালু পজিটিভ এন্ড ইউ আর অ্যাডিং देम টু ফাইন্ড দ্য নেট ফিল্ড বাই দ্য ওয়ে নেট ফিল্ড বের করার নিয়ম কি net potential net field anything if you want to find net right what do you add them right দুইটার ভ্যালু কি পজিটিভ না if you keep adding positive values can you get a zero no not possible right so তার জন্য হচ্ছে you get a low value here so based on this logic can you tell me how the graph look like for a plus and a minus yes so তখন যেটা হবে it will actually touch here and it will go to the other side like that কেন because এখন তো নেগেটিভ হয়ে যাচ্ছে বা পজিটিভ হয়ে যাচ্ছে in this case it's actually going to be the other way around and I'm going to draw the graph right now তোমাদেরকে বলতে হবে the mistake that I made here কি মিস্টেক এখানে বলতে পারবা সো এটা কেন নেগেটিভ হচ্ছে আগে বুঝাই একটু নেগেটিভ মানে কি মাইনাস কে কিউ বাই ডি এর মধ্যে আমার চার্জ নেগেটিভ না so shouldn't the potential start from a negative value and what is my charge here positive so k q by d যেখানে q positive তার জন্য একটা পজিটিভ ভ্যালু আসছে so I understand it goes from negative to positive here and it must make a what in order to do so a crossover right so that's all fine but there's a mistake here it won't be flat না বললো you don't think it's going to be flat মানে এরকম আচ্ছা বুঝছি মানে এই যে সামথিং লাইক দ্যাট কেন very good that's the answer okay this is two opposite charges between two opposite charges what can't exist a null point and since the gradient of my graph gives you the field strength right can I have a zero gradient on this graph no but I'll have a what gradient though at the crossover point a very low gradient because I'm তোমাদেরকে এখন হচ্ছে ওই আগের গ্রাফটাকে দিয়ে দেখাবো because I found students find the comparison here easier so remember these two graphs that we had এগুলাকে দিয়ে তোমরা ওটা বের করতে পারবা that's why I tell students that normally যেটা করবা you just remember one set of graphs and then the other one naturally চলে আসবে okay so let me show you কি করতেছি এখানে so the differentiation of what graph gives you which graph when our differentiation of one graph will give me the other graph is it the differentiation of the field strength that gives me the potential graph or is it a differentiation of the potential graph that gives me the field strength differentiation of the this potential graph will give you field strength yes because if you differentiate money change in y by change in x so if you differentiate the potential graph with respect to displacement or distance what do you get electric field strength be it the negative value but at least you know the shape right so এই গ্রাফটা দেখো আমার যদি হচ্ছে এইটা আমার গ্রাফটা হয়ে থাকে and I differentiate this graph you will definitely get, sorry, if you differentiate this graph, right, you'll definitely get this graph. I'll show you all with a reason, okay? Do you see that this is a what gradient? Negative. So do you see there's a negative value here? Do you see this is a positive gradient? Do you see there's a positive value there? Do you see that the center has like a low value, but not a what value? Zero value. Do you see the center here has a very low gradient, but not a what gradient? Yeah, zero. Okay, so if you can remember one of these graphs, then the other should be easy. Why? Because if you differentiate this graph, you should get that graph out there. Okay, so similarly, how does the other graph look like? So let's say if the differentiation of this gives you that or not. Okay, so yeah, let's look into this. So this is a what gradient? Negative. What is that gradient? Negative. Do you see that the start gradient and the end gradient are the same type? Either negative hote pare, positive, positive. Because this graph could have been very easily that graph as well, where my gradient would have been what at the start? Positive. And what would that be as well? Positive. So do you see that the values at the start are always going to be the same? And do you see at the center, you cross this point here, which is a null point. A null point is the point where you have what net field strength 0, which is like here where the gradient is 0. Okay, so এটাকে differentiate করলে তুমি এটা পাবা. Right, so these are the graphs out there. I mean, additional information লিখে দিচ্ছি, but the concept that you need to understand is that you can check for yourself in the exam. You're given a graph, is it right or wrong? So এটা যেহেতু potential versus distance graph, তুমি এটা কি analysis করবা? Gradient. And gradient কি হচ্ছে electric field strength versus distance graph match করে নাকি ওটা check করবা. Match করলে হয়ে গেল. So yeah, these are all the graphs that we have, and with that, that's the end of electric field strength. But yeah, graphs go to Chamilar. The more you do, the more accustomed you become. Okay. This one. Why is it like this? So this is V versus D, right? What does the gradient give you? Electric field strength, right? And this is a minus and a plus. If you remember, if you have a plus and a minus, at the center, there can't be any null region because the plus is repelling you and the minus is attracting you, right? Aren't both the forces acting in the same direction? Is it possible for you to nullify the forces? So nullification of force can only happen when both of them are what charges? Like charges. So if you have a plus here and a plus here, and you have a plus charge here, isn't the plus pushing it this way? And isn't that plus pushing it the other way? So there can be a place where they cancel out. In this particular scenario, there can't be any cancellation. However, as you start to move away from one of the charges, right? Aren't you going far away from this charge? And aren't you far away from that charge as well? So somewhere around the center, you have the least electric field strength. It's supposed to be a very low value, but it can never be a what value? 0. So to signify that in your graph, as we go near the center, we end up having a very low gradient here, but we can't have a what gradient? 0. Which is, by the way, completely possible here, because this is a graph between what charges? Like charges. And in a graph for like charges, there is a region in the center where your electric field strength is actually what? 0, right? So you must have like a flat here, like a turning point. Right.